Okay, let's start the last session today. Next speaker is Hao-Wei Huang from National Tsing University. He will tell us about support problems for free convolutions and applications to quantum information theory. Please start.
Yeah, thanks. Okay. Okay. Thanks for the invitation, for giving me this talk, and thanks for the introduction. Today I will talk about something about quantum information theory, especially the research field of non-commutative probability space to this QIT. And this is joint work with Benoit Collins. Sorry about that. I put the name in the wrong order, in the reverse order. That should be Benoit Collins. All right. So in today's talk, I will introduce the background, and then I will introduce non-commutative probability theory, and then I will tell you the applications to quantum information theory. So first of all, let's talk about, let me introduce the motivation. Assume that you have a map phi, which map from n-by-n matrices to itself, and it's a adjoint preserving linear map. And this map phi is called K positive if you tensor phi with the identity map on the dimensional K space is still positive map, then this map phi is called K positive. And here we say positive, it's a positive map, which means it maps positive elements to positive ones. And actually, when I say positive elements or positive matrices, what I mean is positive semi-dependent matrices. So for simplicity, let me just call it positive elements or positive matrix. Then in quantum information theory, it doesn't work. Okay, thanks. So in quantum information theory, people work with choice matrix, which defined in this way is a sum of EIJ tensor phi EIJ. And you can translate the K positivity of the phi into the conditions on the choice matrix, which is the following: is K positive if only if the product of these three maps or matrices, especially identity tensor orthogonal projections of rank K on the n-by-n matrices is still positive element. And important notion about K positivity is complete positivity, which means a phi is K positive for any K. All right, so let me introduce Schmidt's rank. First of all, we have a bipartite pure state, which is in Cn tensor Cm. And we have the Schmidt decomposition. Namely, we can decompose C into the simple tensor product in Cn tensor Cm. And EI and Fi are also normal sets in the corresponding spaces. And you want to maximize, you want to find the minima of the sum of the number of the sum. If you can do so, this number R is called Schmidt rank of this bipartite pure state. So let me use the SR C to denote the Schmidt rank. Or you can use also normal basis EI tensor Fj. Here, the difference between these two representation is that you use the same index, but here you choose also normal basis in the Cn times m. All right, so let me introduce basics in quantum information theory. A positive element is called density matrix if, of course, it's a positive element, and it has unit trace. And it's co-separable if we can write it as a simple tensor product, a convex linear combination of simple tensor products, which means here Pi is positive because it represents probability, and the sum of all probabilities is 1. And this is simple product, a simple tensor product. If you cannot represent low in this way, then it's called entangled. So this is quite straightforward. And now this slide, I will tell you some property about entangled states and separable states. A pure state is separable if only its Schmidt rank is 1. And this is one of the most example entangled states. So here comes the problem in quantum information theory: how to detect, how to verify whether a state is entangled is very important, or you can say is one of the central problems in QIT. Actually, it's very hard and it's very challenging. So the Schmidt number tells you how entangled a state it is. Namely, you have to choose, the Schmidt rank is R, you have to choose at this R mixed pure state to represent the entangled state. So in some sense, this Schmidt number tell you how entangled the state is. So now let me combine entangled states and K positive maps. So here I say that the positive maps provide a fundamental tool to detect entangled states. More precisely, if you have a K positive map, then if you plug in a state with Schmidt rank less than or equal to K, K here is the K positivity of the linear map V. Then if you have this positive element, then this result, you always have the positive element. And the converse is the converse means that if you have a state so that you plug in into the by tensor ID, you get a negative non-positive element. That means this state has Schmidt rank greater than K. Okay, so this is if only if condition. So here I put some inclusions. So you have a CP map, which means it's K positive for any K. And in the middle, you have K positivity. So this inclusion tells you how you test entangled states. So now, I think I started the talk at 4:10, so I have 30 minutes. Okay, I still have 20 minutes. Now let me introduce another research field, which is random matrix and free probability. And now today I will tell you some applications of this research field to QIT. So in large dimensions, K productivity of maps can often described by spectrum of the random matrices, and this leads to a connection to free probability. And I will introduce the so-called free probability theory and how to apply this theory to QIT later. I just want to tell you the motivation. And there's another important property about random matrices, which is asymptotic. Suppose you have a random matrix which converts to some random variable, say little x. So this is quite known because you just compute the moments, which means the nth moment of the random matrix xn converts to the corresponding moment of the little x. And in 1988, Roy Glasgow found that if you have two independent random matrices, each one of them converts to some random variable, say x and y, when the size of matrix tends to infinity. Now you have independent random matrices, but at the end, when you tend to infinity, the limiting law or limiting random variable obey a very special relation, which is freeness. So this is why it's called asymptotic freeness. And I will introduce that later. So now let me tell you the definition. Not exactly, but I will tell you how the concept of freeness. So suppose we have a measure which is complex supporting a real line, and let's pick a random variable x, which is infinity, and it follows the distribution mu. Now let's consider free product. It's very abstract, but I can tell you what it is. So now you have a random you have n by n matrices, the algebra, and free product is the L infinity, and this is expectation, normalized trace. Another expectation is natural expectation. The free product is quite, you can describe in the following way. You collect all alternating words, like A1, x1 squared, A2, x2. A1, A2 are from n by n matrices, and x1, x2 are from L infinity. this space, over x1 squared, a1, x2 cube, a2, so on and so forth. You simplify, you get a reduced words, something like that, and they are alternating, because if you have x1 times x1, you put in together, you get x1 squared. So you can say, if you collect all possible reduced words, and that will be, you will get a free product of these two algebras, and together with normalized expectation. And the next step will be computing the mixed moment like this. You want to know the moment of this, the mixed moment of this, the product. And there's a universal rule to compute the mixed moments. And the mixed moments are completely determined by the restriction of the tau tilde to n by matrices, which is normalized trace, and infinity, which is classical expectation. So even I tell you how, even I didn't tell you the precise definition of freeness, but right now you can get, well, you just get the reduced words, and now I think you can get at least you know how to simplify this, because there's a universal rule. Even I didn't tell you that, but you can mention that there's a rule governing how to simplify this mixed product. And now I consider compressed algebra, namely this, you have the biggest space, M tilde, and now you project onto the left corner E11, which is the elementary in n by matrices, which is 1 in the left upper corner and 0 in other entries. And this is expectation, because you want to get if you put in identity, you also get a constant 1. So this normalization is to make what I said happens. All right, so now I put these two subjects together. Namely, originally you have a linear map which maps n by matrices to the same one, but now I replace n by matrices by the compression, the compressed probability space M here. So the definition is in this way. I mean, EIJ is mapped to E1I, X, EJ1. So this is a free product. This is reduced words. Even they are from different algebras, but now you can regard a product as one element in the free product space. So this is reduced word. And if you want to compute a mixed moment, remember you have a universal way to simplify the mixed moment. So even I didn't know what it is, but imagine you know what it is. And now you can consider the choice matrix. The definition is exactly the same as the standard choice matrix, namely EIJ tensor product with phi mu of EIJ. And again, you can translate the K positivity of this map phi mu into the choice matrix. And the formula is exactly the same. The condition is exactly the same. As before, you have to check all rank K orthogonal projections, either in the random matrix, in the n by matrices, or in the approximative your batch. All right, so next time, let me introduce another map, which is R. Again, this is the largest algebra, which is a free product of the n by matrices and infinity. I define R, which maps from M tilde to Mn tensor M. And the definition is actually this is a choice matrix of the of phi mu right here, but I just write it down explicitly and I call it Ry. I'm sorry, this is a typo. This should be X. If I say X, this should be X. If this is Y, then this is Ry. So this is a typo. This should be Y. So whenever I pick an element Y from M tilde, the larger space, this is the choice matrix, and I just call it Ry. And the good thing is that you can check that directly, or you can take it for granted. R is an isomorphism, namely R of xy is R of x times R of y. By definition, you can check that directly. And it's a star map, which means R of y star is R of y star. So this is a good property of R. And because of this isomorphism, and we can compute the moments, namely you want to know the R of y to the power n, and you plug in the expectation, And in this space, the expectation is trace R and normalized trace and tensor tau. It turns out that they share the same distribution, namely they have the same moment. I mean, this quantity is equal to tau tilde y to the n. All right. Tau tilde is the largest space. This is the free product. So tau is the normalized. You multiply tau tilde by n. So here the identity of m is E11. So now you plug in E11, you expect to get constant 1. But if you plug in E11 into tau tilde, by this restriction, you get 1 over n. So that's why we multiply the outcome by n to get a constant 1. Because you expect to get that, you plug in identity, you get constant 1. So that's why we multiply tau tilde by n. Yeah, thanks for the correction. And then, yes. So let me jump to the free edit convolution. So before I tell you that, let me tell you the classical convolution. Suppose you have two classical independent random variable, x and y, and you know the law of each random variable. And now you compute the sum, x plus y. And now you want to know the distribution of the sum. And the classical property tells you there's a rule, again, it's a universal rule to tell you how to compute the distribution of the sum. And now we just replace the classical independency by freeness. So again, as I told you in the previous slide, there's a universal rule to simplify the mixed moment. Particularly, this is a sum. So x plus y to the power n, it's a special case. So again, it's a universal rule to compute the sum, the distribution of the sum. So it's completely determined by the laws of x and y. Even I tell you how to, I never told you how to determine that, but imagine that you know how to do that. So more precisely, there's a universal way to compute the distribution of the sum. And it depends on mu x and mu y. So in the literature, it's used box plus to denote this kind of new convolution. So here I said it's analog to classical independency and classical convolution. All right, so you can say you compute the sum of x and y, and x, y are independent and identically distributed. So it's a classical convolution twice. And here I just replace the classical convolution by free convolution. So the third convolution power, you do the same thing. And in free probability, you can extend this convolution power into a semi-group. Namely, this number t can be real number greater or equal to 1. It's not necessarily an integer. All right, so this is done by a whole bunch of people and in 1990 or 20. Sorry. All right, now let me introduce another distribution. You multiply the random variable x by c, and the distribution I denote by dc mu. So this is dilation. All right, so now after that introduction, let me come back to quantum information theory. So in 2015, Collins and Hayden and Nikita, they consider this map and determine when this map is K positive. And the result is the following. This map is K positive if only if the support of the measure mu with this conversion power is this measure is supported on the positive real line. So in other words, they convert a K positivity problem to the support problem in free probability, especially this kind of free conversion power. And they also use this kind of abstract setting to study entangled states. So, for example, if this is not positive, then this law is entangled. So this is quite even it's quite abstract. I tell you that this is quite abstract, but you have actually they have random matrices to realize this kind of structure. So this is not not so abstract. And in the same paper, they use the same map or random matrix to construct a random matrix or a density matrix, whatever. It's not if you take a partial transpose. Sorry, but I didn't introduce partial transpose. You can imagine that you can take a partial. You can take a transpose on each block. If you write the matrix into the block form, you take the transpose of each block. It's called partial transpose. And if low is if you take a partial transpose of low, if you get a positive matrix, and it's called PPT, which is a positive partial transpose. And now people want to know, can you find whether we can find a density which is a PPT, but it's entangled and it's durable. They use random matrix technique to construct this kind of states. So modularity K positive free maps can be used to detect states which with Schmidt number greater equal to K, greater than K. All right, so up to now, you know that they convert a problem into free property problems, especially support problem is very important because they kind of stop here. I mean, because you need to know how to analyze the support, especially the minima of the support is 0 or greater than equal to 0. So this is what I do. This is what we do in 2026. We try to analyze the support of free convolution. So we developed a systematic method to determine the minima or maxima of the support of the distribution, especially free eddy convolution. So this is the first step, because if you want to go further, you have to solve the support problem in the middle. And next, let me introduce a condition on the choice matrix C5. This is spectrum decomposition, but I put the same. I put the eigenvector together with the same eigenvalue. So this is the eigenprojection decomposition of C5. So these projections are orthogonal. If you have different index, then they are orthogonal. So in 2016, Nikita put this kind of, well, let me introduce the condition. They introduced unitary condition on the choice matrix C5. Namely, if you take a partial trace of the projection PT, you get a multiple, you get a constant multiple of the identity matrix. So they call this kind of condition UC. Or this tells you if you take the projection adding on any vector and inner product with the same vector, you get the same constant. So that's why they call unitary. It tells you they spread the weight on the eigen projection equally. So when you see maybe you think it's a very strong condition, but actually it's not. Transpose, the operational taking transpose is satisfy UC and reduction map. And actually, I just put the 2 examples. Actually, in the paper, they provided several examples satisfy UC. So the advantage of this kind of map is to construct PPT and entangled states very easily. So that's the purpose of introducing this kind of map. So let me continue. Remember, we have the star isomorphism R, and we have the phi tensor identity of the algebra. This is a new random variable, and let me use T phi mu to be the distribution of this new random variable. And actually, under UC, we know what this distribution is. Actually, it's a convolution of a whole bunch of convolution powers. First of all, you have the computational power is from a rank of the projection PT, and you have to dilate this measure a little bit, and it's based on the eigenvalue of the choice matrix. And then you have another convolution. All right, so this is followed. Oh, sorry, and let me go forward. Yes. So under UC, we proved that suppose you have two linear maps, P and psi, and now we tensor P and psi and compute T of this tensor product. It turns out that we can convert the tensor product into the composition. And we can say this is quite good property because, as you know, if you want to deal with the tensor product, sometimes it's very complicated, but we believe that if you can convert the tensor product into the composition, this identity would help us to deal with some problems in quantum information theory, because the difficulty of the problems in quantum information theory mainly comes from the tensor product, the complicated structure of the tensor product. And we proved that, yeah, I will finish that soon. So we also proved that if phi is CP, if only if the support of T phi mu is positively supported on is supported on the Pauli real line for any measure mu with the same property. And T phi has a fixed point with the same as circular law. Sorry about that, I didn't introduce the law, but there's only one fixed point. And we also attempt the central limit theorem. I think this property will help us to understand some problems in quantum information theory. All right, so I think I can spend 1 to 2 minutes to introduce the main application. I think this is the interesting part. Phi is from Mn to Mn. It's a quantum channel, and we have input. And this is P Rayleigh entropy. And I think some of you may be familiar with that. So let me say that very quickly. And in quantum information theory, they want to know the minimum output entropy, which defined in this way. So in classical information theory, if you consider the classical channel, you have the identity. But in tensor world, you will get a violation. But the problem is, for what value of P you will get a violation. So this is the main problem. They want to get a violation, but the problem is what the values for P will you get the violation. So the technique is quite simple. In 2026, they consider the projection Hao random projections. So here you pick Pn, and the Pn the rank satisfies this condition, and C phi or phi they put UC condition on C5. And as I introduced in the previous slide, you can, if you take a limit, you know how to compute the distribution. It tends to this kind of free convolution. And because you take the projection, so the distribution of projection is nothing but a Bernoulli distribution, because the spectrum is 0 and 1. So in other words, they prove that the maximum eigenvalue of this map tend to the support, maximum support of a distribution. So they use this kind of techniques and pre-probability theory to get a violation. And the P is greater or equal to 3/4 or between 0 and 1/4. So there's one gap. I mean, bigger than 1/4 and less than equal to 3/4. The problem is still open. So this is what we want to do next, because we believe that our results should be helpful to solve the problem. And because we know how to analyze the support. And we believe that based on these two known facts, we can change the operator, change the projection to arbitrary random matrix, arbitrary matrix, which are positive and states. And based on we know how to analyze the support, we believe that maybe there's some hope to improve the result, or you can generate more concrete or more examples, not only projection, satisfy this kind of condition. So here on this slide, I put some words like a free person or freely infinitely divisible loads can do something new. All right, so this is my talk. Thank you very much. Yeah, it's a good question because I hope so, but I don't spend time on this kind of problem. But I didn't tell you that, but this kind of technique, I mean, the application of free probability and random matrix to QIT is just 10 years. So there are so many people, so many problems to work on. So I don't know the answer right now. But according to my knowledge, there's no such kind of result in the literature. Yes, it's a good question. I don't know the answer, but we can check it now. Yeah, we'll check that.
Question? I have a question.
Yes.
So this time we totally related to quantum scale. We have some comment on function.
I'm sorry.
Quantum scale.
Quantum chaos.
Criterion.
Yeah, again, I don't know that area, but I believe that there's some application. Maybe some people working on this area, they want to know the connection.
Related to freedom complex.
I see.
And the way you propagate the
I see. But I believe so. There must be some connections. Yes. Yeah, I believe that people are still working on that.
Okay.